All right, so today we will begin the beginning of unit number 3, which is human evolution. And we will go over chapters 9 this week, chapters 10 and 11 the week after, and then chapter 12. So chapter 9 through 12 are the ones that will go over the last 6 million years of human evolution, essentially. There are a lot of details in these chapters, so more so than any other chapter in the past, I do really recommend that you take your time with the reading, make flashcards for yourself. So anytime you see a bold term, write the term on one side and then the definition on the other, and then practice those terms. And of course, take really detailed notes as we make our way through the PowerPoint presentations. And don't forget, the recordings of these are available in Canvas. So if for some reason you miss a lecture or you miss a detail, or if I'm going too fast, if I'm going too fast, just tell me to slow down. But if you miss a detail, you can always go back to the modules and get those details later on. Okay, fair enough? Yes? Okay. All right, so our first chapter, this will go along with chapter 9 in your textbook. So we're going to look at the origins of hominins. So that term hominin just simply means human ancestor. And we will also look at the origins of bipedalism, or locomotion predominantly on two legs. All right. So essentially, how do we know if a fossil belongs to a human ancestor or a hominin? So we will talk about many traits that identify what it means to be human, but set that foundational, or sometimes called hallmark, characteristic of what it means to be human is bipedalism. So that's essentially the earliest or the first anatomical trait that we can identify in the fossil record that separates the hominins from the pongids. So hominins is just a member of the group, including humans and our fossil relatives, since the point at which we split from the other apes. So hominins, hominidae, includes humans and our ancestors, and then the pongids include the other great apes, the chimpanzees, bonobos, gorillas, and orangutans. So we know that somewhere between 5 to 7 million years ago, we see a divergence in our evolutionary tree. So the hominins go off in one direction, pongids go off in another. So that foundational or hallmark characteristic that split the hominins from the pongids is the anatomical adaptations for primarily bipedal locomotion. So this wasn't a change that happened overnight. This is a very gradual transition. So we see the earliest evidence for what we call habitual bipedalism or part-time bipedalism about 6 million years ago. Okay, but we don't really see evidence for full obligate, full-time bipedalism until about 2 million years ago. Okay, so this is a change that took millions of years. And we know that the earliest bipedal hominins were practicing both, most likely. They were bipedal when traveling on the ground or standing on stronger branches to reach higher hanging fruit. However, they retained some of that ability to be arboreal. So they were likely doing both. They were swinging from the trees, they were practicing brachiation, and they were also practicing bipedal posture and walking when traveling on the ground or standing on stronger branches to reach higher hanging fruit. Okay, so we know that they've displayed these transitional or habitual forms of bipedalism because we see that the very earliest hominins, like Sahelanthropus chigensis and Ardipithecus ramidus, are going to display something called a mosaic anatomy. So you're going to hear that term come up a lot over this unit. That term mosaic simply means a mixture of primitive and derived features. So recalling back to when we learned classification, know that primitive means an older trait, and then the derived feature means a newer trait or emerged more recently in our evolutionary past. So we're going to watch a video clip here, example here in a moment, but we're going to look at an example of one of the earliest bipeds, Ardipithecus ramidus, that's displaying a really mosaic mixed anatomy. So we're going to see that the pelvic girdle, so what makes up our pelvis, so the two os coxae, and then also the sacrum and the coccyx. I wish I had one here to show you, but just know that that pelvic girdle, the top half is going to be much more like a biped. And then the bottom half is going to be long and narrow like you would see in a quadruped. So the pelvis itself is mosaic. You're also going to see features like longer curved phalanges. Those are the finger bones and the toe bones. So that's a retention of that ability to grip the branches. So that's more of a primitive characteristic. So that's indicating that Ardipithecus was still able to locomote in the trees and still relied on arboreal locomotion at least part of the time. Also, Ardi is going to have an opposable hallux. The hallux is the big toe. So like for humans, of course, we have an opposable thumb and our big toe is not opposable anymore. Our big toe is in line with the rest of our toes. But for this early hominin, for Ardipithecus, we're going to see that Ardipithecus has opposable thumbs and opposable hallux. All right, let's watch that little video clip. It's going to be a short one, another one from HHMI Biointeractive Videos. It's going to show you the evolution of bipedalism. So while you're watching this clip, I want you to pay close attention to why this is considered to be a mosaic anatomy. What about Artie's anatomy makes her a mosaic? Okay. And what does this say about the earliest bipeds? So think about why would this adaptation emerge? What would be the evolutionary purpose or advantage? Let me find where my clips are. All right. Here we are. All right, so I want you to think about, what does the term mosaic mean? Why is Artie considered to be mosaic? And what is the evolutionary purpose of this transitional form of bipedalism?
Professors, there's no sound on the clip.
All right. So, what
If I'm
about Artie's skeletal anatomy? What makes her a mosaic? What makes us think that she had a transitional or habitual form of bipedalism?
professor, there was no sound in that clip,
Really? Okay.
really.
All right, I'm sorry about that, you guys. I must have forgotten to optimize for sound. Let me stop the share for a second and let's go back and do it again. Okay, I'm sorry about that, you guys. Do you want me to replay it? Or were you able to follow along with the captions?
Yes, please replay it.
Okay, let's go ahead and watch it again. All right, so hopefully, let's see if it's working now. All right, let's start it over again.
Walking on two legs marked a
Working.
huge
Are you able to hear sound now? Yes, okay. Thank you guys.
change for our species. In fact, being almost exclusively bipedal makes us unique among our primate cousins. The question is, how did our ancestors start spending so much time on two legs? A fossil found in Ethiopia revolutionized our understanding of this transition. I'm in Berkeley, California to meet Tim White, one of the leaders of the team that discovered Ardipithecus ramidus, Artie. The team was digging in the Afar region in Ethiopia. Then, in 1994, a graduate student named Johannes Haile Selassie found a fragment of hand bone in 4.4 million year old rock.
He picked up and said, "This looks like a hominid." So we scraped and brushed that surface, and we found some of these hominid hand and foot bones in place. And so we focused on that little hill.
This was a hugely significant find, a new species of hominid from a time when scientists think our ancestors were becoming bipedal. It took experts about 15 years to fully piece her together. Biologist Owen Lovejoy has been figuring out how Artie might have moved.
The critical thing in bipedality is the structure of the pelvis.
The pelvis was crushed during fossilization. From its reconstructed form, the team was able to deduce how Artie likely moved.
This is a plastic structure that's produced by a three-dimensional printer.
Cool.
The top part of Artie's pelvis looks more human. The hip bone is short and broad, a key indicator of bipedalism. But the lower half is much longer than a human pelvis, more useful for climbing. It suggests that Artie was a creature in transition. She could walk on two legs, but not as well as you and I. Her feet support this idea.
This thing had full grasping ability.
So she has a grasping foot that can walk.
Yes.
It was a mosaic of anatomy that had never been encountered before.
So while not as nimble on 2 feet as we are, Artie was a much better climber. But it wasn't just her body that came as a surprise. It was also her environment. The team collected around 150,000 additional fossils. Wherever they found Ardipithecus bones, they found woodland creatures, parrots, monkeys, and peacocks, as well as woodland plants.
It was a woodland, not an open savanna setting.
Now that's a
These
surprise.
are woodland animals.
That runs counter to so much of
It
what
runs counter
people
all the way
expect.
back to the 1800s.
So now we have a new, detailed picture of how our ancestors made the transition to bipedalism. Artie was a woodland creature. Small, just under 4 foot tall. She was a good climber, using all fours when in the trees. But she walked upright when on the ground. Our ancestors started walking on 2 legs while still living in the woods. Artie suggests that by 4.4 million years ago, the transition to walking on 2 legs was already well on its way.
All right, so what about Artie? What about her skeletal anatomy makes her a mosaic or a transitional form of bipedalism? Well, let's start with, what does mosaic mean? What does the term mosaic mean? So when referring to fossils, the term mosaic simply means a mixture of primitive and derived features. So a mixture of those traits that are older combined with those traits that are newer or evolved more recently in evolutionary time. So Artie is a mosaic because she has some features that indicate a retention of arboreal or tree dwelling, combined with features that indicate obligate bipedalism or habitual bipedalism, I should say. So another thing that was a surprise with Artie was the fact that she lived in a woodland, because in the 1970s, when we were first exploring the origins of hominins, it was believed that bipedalism emerged on the open grassland or open savanna. And we'll talk about the savanna hypothesis here in a moment, but it was a surprise to realize that bipedalism emerged in a mixed woodland environment rather than on the savanna. So that's another thing we'll talk about in this lecture. So let's talk about the types or degrees of bipedalism. So occasional bipedalism is just like it sounds. Occasional bipedalism would just simply be bipedal locomotion that is practiced sometimes. So examples of organisms, of species that practice occasional bipedalism would be the great apes. So chimpanzees, bonobos, gorillas, and orangutans. So just like it sounds, they will occasionally stand and even locomote bipedally. However, they definitely rely on other forms of locomotion as their primary means of movement. So the primary means of movement for a chimpanzee or a bonobo, for example, is brachiation in the trees, knuckle walking, and only occasionally bipedalism. Also, if you're watching an ape at the zoo, like a chimpanzee, you'll notice that, yeah, sometimes they do stand or walk bipedally, but it's generally only when they're carrying something, when they're carrying food or infants, and they're not using it as their primary mode. When they're moving around on the ground, they're primarily using knuckle walking. So they only resort to bipedalism under certain circumstances. Okay, so there's some examples here. You see a chimpanzee standing bipedally in the trees, and then you see a chimpanzee here walking bipedally to cross a river or a stream. Okay, so you're really, just like it sounds, occasional bipedalism just means something that you see occasionally, but that's not their primary mode of locomotion. All right, the next type that we'll talk about, or the next degree, is called habitual bipedalism. So we believe that Artie, the film clip we just watched, we believe that Artie was a habitual or part-time biped. And we also believe that most of the Australopithecines that we'll learn about later on in this lecture, we believe that most of the Australopithecines were also habitual or part-time bipeds. So habitual bipedalism is simply bipedal locomotion that is practiced regularly, but not full-time. So you can think of it as part-time bipeds. So the habitual bipeds are still relying on other forms of locomotion. They're using bipedalism and arboreal climbing equally. So Artie is a perfect example of this, because you see that very mosaic anatomy. You see a pelvis that the top half looks more like a biped, bottom half looks more like a quadruped. Longer arms, curved finger bones like you would see in a brachiator, and an opposable hallux and big thumb. So they have both opposable thumbs and halluxes. So this mosaic anatomy was somewhat surprising, because we once thought that this bipedal locomotion was a transition that happened around 3.5 million years ago. But once Tim White and other anthropologists discovered these, what we call pre-australopithecines, so those hominins that came before the australopithecines, it really changed our ideas on the origins of bipedal locomotion. We now know that this transition took millions of years. So this transition likely began around 6 million years ago, but we don't really see this transition fully complete until about 2 million years ago. And we know that these earliest bipeds lived in this mixed woodland habitat rather than on the savanna. All right, then the full-time bipeds are going to be called obligate bipeds. So obligate just means full-time bipedal locomotion that is practiced exclusively. So finally, we are to the type of locomotion that we as modern humans have. It's obligate bipedalism, essentially means full-time bipedalism or locomotion that is practiced exclusively. Obligate bipeds do not rely on other forms of locomotion. So essentially, we consider Homo erectus and onward to be obligate bipeds. So that's about 1.8 million years ago, all the way up to present. So we'll look at the anatomical features that indicate fully adapted to bipedal locomotion, such as longer femurs that have a bicondylar angle, a short, broad pelvis, a hallux or big toe that is in line with the rest of our toes, and an S-shaped spinal column. Okay, so obligate bipedalism is what we're going to see in Homo erectus and onward. So we won't really get to Homo erectus until likely next week, possibly even the week after, but just know that that's coming. But basically every hominin we cover in this lecture today is going to not be an obligate biped, but a habitual biped. So remember, habitual bipeds are part-time bipeds. Obligate bipeds are full-time bipeds. Do we have questions so far?
Yes. When was Artie discovered? Was that 1970, did you say?
Artie was discovered in the early 90s. Artie was discovered in 94.
94.
I believe so. I'd have to look at the exact date. I believe it was early 90s when Artie was discovered. But
And-
also wasn't fully published until the early 2000s.
Okay. How far did they have to dig? Is there information on that to find her?
I mean, I would have she was found in the Hadar region in Ethiopia. I would have to look, typically when these things happen, there are excavations that are going on for years, sometimes decades.
Sure.
But I would have to look into the details of that for you. But good question. Other questions?
Oh, yes. I'm sorry. I have one more question.
Sure, go ahead.
What is where will we find Artie? What species is Artie today?
Well, all of these species are now extinct. So as we start going through all of these species, we will see that many species coexisted and likely interbred with one another. But these species that we're learning about right now, these are all extinct species of hominins. So at the very beginning, when we were talking about the evolutionary tree, that we need to kind of erase that image of a chimpanzee here on this end and a modern human down here on this end, because that's really a misrepresentation of how human evolution works. We need to start thinking of it as branches of a tree. And so every single branch is indicating a different species or group of species. So these are all branches on the tree that are no longer, it's very possible that the species that coexisted at that time are interbreeding, but we don't have an Artie. There's not an Artie left today. It's possible that in our genomes, we have the remnants of these early hominins, but these are all extinct groups of hominins that we're learning about right now.
Thank you.
You're welcome. Good question. Other questions? Nothing? Okay. And we will pull out some evolutionary trees so you guys can see a kind of visualization of what this looks like. Okay, so let's kind of break down what the bipedal adaptations are. So there's really 5 parts of the human skeleton that really have some critical changes once we see this transition, once they've fully transitioned from the habitual to the obligate bipedalism. So the foramen magnum, that's the hole where the spinal cord will attach. So it's at the base of the crania. So if you're looking at a quadruped, this is a gorilla here, and here's a modern human here. So the foramen magnum for the gorilla will be more posterior. That word posterior means towards the back of the skull. So for the gorilla, the foramen magnum is more posterior to allow for this quadrupedal posture. For the human, the foramen magnum has moved more anterior, more towards the front of the skull, that allows for this upright bipedal posture. The vertebral column we're going to see is going to have an S-shaped curvature. And we're also going to see that the lumbar vertebrae are significantly larger in the biped. The lumbar vertebrae are those vertebrae in the lower back. And they're larger in the biped simply because they are supporting more body weight. We'll look at the pelvic girdle, and more specifically the ilium, the 2 parts that make up the pelvic girdle. In the biped, you're going to see a shorter, broader pelvis, whereas in a quadruped, you see a longer, more narrow pelvis. We'll look at the femur. That's the bone, the long bone in our thighs. So the femur of a quadruped, like a gorilla, is going to be very short and straight, whereas the femur of a biped is going to be longer and it's going to angle in medially towards the knee. So medially means towards the middle, and we're going to call that the bicondylar angle. And we'll also look at the hallux, that's the big toe, and the phalanges, those are the toe bones. So the hallux, so we have, as humans, of course, we have opposable thumbs. But a chimpanzee or gorilla and even Artie is going to have an opposable big toe as well. And also some of the earliest bipeds are going to have longer and curved phalanges, whereas more obligate bipeds are going to have shorter and straighter phalanges. All right, so here's a little bit more detail. The foramen magnum, essentially that hole where the spinal column will attach. So for apes, for quadrupeds, it's going to be more posterior or towards the back of the skull. We'll also look at something called the location of maximum skull breadth. So let me pull a few examples out for you guys. So we've got our gorilla skull here. So the foramen magnum. So that's the hole where the spinal cord would attach. So it's more posterior in our gorilla here, more towards the back of the skull. The location of maximum skull breadth. So when you look at it from the back, you're looking for the widest point. So for the gorilla, the maximum skull breadth is going to be down here at the base. Whereas for a modern human, the widest point for our skull is all the way at the top by the parietals. So the bones, those of you not in lab, just as a review, the bone in the front here is called the frontal bone. Top sides is called the parietal. The one all the way back is the occipital. So for modern humans, our maximum skull breadth is all the way up here at the top. Okay, presence of postorbital constriction. So the orbits, those are the eye sockets here. So postorbital constriction is how far does it sink in or tuck in behind the brow ridge here. So you can see with the gorilla, there's a pretty extreme, what I would call extreme degree of constriction, because you see the brow ridge here, the supraorbital ridge, and then you see it sinks in to a pretty extreme degree behind those orbits. Okay, we call that postorbital constriction. And then in comparison, let's pull out Homo erectus here. So Homo erectus is going to have an anterior position of the foramen magnum. So it's moved closer to the front of the skull to allow for this bipedal posture like this. The maximum skull breadth, it's not quite as high as ours, but it's moving higher. And then also the postorbital constriction, even though it's still there slightly with Homo erectus, but you can see it's not nearly as extreme as what we saw with the gorilla, okay? And then by the time we get to modern humans, everybody feel your own skull, start at your brow and then feel up to your hairline. We have full lack of postorbital constriction. So the reason for that, or what that tells us, is that the frontal region of our brain is much larger than that of Homo erectus and definitely much larger than that of the gorilla. Okay, we have a larger overall cranial capacity, and more specifically, we have an increased size of the frontal region of the brain. Questions so far? Feeling good? Okay. All right, so the vertebral column, like I mentioned, in the quadruped, like a gorilla or chimpanzee, we have a C-shaped vertebral column. And all of the vertebrae will be approximately the same size because they're all sharing an equal amount of weight, because they're quadrupedal, because they have the support of all four limbs. There's not necessarily one vertebrae or one section of vertebrae that needs to support more weight. Whereas a biped will have that nice S-shaped vertebral column, and the lumbar, or the vertebrae in our lower back, must be larger because they're supporting far more body weight than those in our neck, for example. And lumbar back pain is still the #1 reason why humans visit a doctor today. So you could even argue that here we are 6 million years later, and we're still not perfectly adapted to bipedalism. All right, so this slide here just shows you postorbital constriction. So it's showing you an example of a lot of constriction. So we've got an Australopithecine here. This is Australopithecus afarensis. So postorbital constriction is how far it tucks in behind the brow ridge. So we see lots of constriction here. And then we've got Homo erectus. There's still some constriction, but it's not a lot. It's less than what you see here. And then the fully modern human, you see that there is no constriction. All right, let's look at the pelvis. So these are images of a chimpanzee pelvis here on the left, and then a fully modern human pelvis here on the right. So you see the overall shape is much longer and more narrow for the chimpanzee, and the overall shape is shorter and broader for the modern human. You'll also notice that the sacrum and the coccyx are much longer and more narrow in the chimp, whereas they are short and broad in the modern human. You'll also notice the bottom half of the pelvis, when you're looking at the ischium here, this section, it's much longer in the chimp, whereas it's much more narrow in the human. Also the iliac blades, so see how they kind of flare outward here in the chimp, and then they kind of round around and form this bowl shape in the modern human. So you'll often see it described or hear it described as modern humans having a more rounded bowl-shaped pelvis, whereas chimpanzees have a much longer, more narrow pelvis. But the pelvic inlet, even though the overall, so don't let this confuse you, even though the overall shape of the pelvic girdle is more long and narrow for the chimp, the birth canal is actually wider for them. So for example, a chimpanzee, a gorilla, bonobo, an orangutan, they have a much easier time giving birth. They don't go through the same pain and difficulty and risk when giving birth to their infants. So one of the evolutionary trade-offs of being bipedal is the overall shape of our pelvic girdle changed, obviously, and also our pelvic inlet, or essentially where the baby's head would pass through, became slightly more narrow. So that's one of those evolutionary trade-offs. So even though we're bipedal, we have more complicated, more dangerous birth process. And also our babies are born, we're larger brained hominins, but our babies are born pretty dependent upon us for survival. Most of that brain growth occurs during age 0 to age 5. The brain size of our infants is somewhat limited in utero, meaning that their brain sizes can't get too large during that first 9 months where they're developing. Because if they do, then they won't be able to safely pass through the birth canal, which without the intervention of modern medicine or C-sections would result in death. So it was important in our evolutionary history that the brain size of our infants didn't exceed the opening of the pelvis. So that's what I mean when I say that the brain size was somewhat limited in utero. All right, the femur, so that's the long bone in our thighs. So when you look at these two femurs together, right next to each other, you're going to notice that one's obviously longer. The femur of the biped is longer, but the most important thing to look at is the angle of it. So the angle here, so we're starting up here at the top of the femur, or what we call the proximal end, where it connects to the pelvis. So that's the head of the femur here, where it connects to the osteobellum of the pelvis. So you see here it starts, and then it angles all the way down towards the knee. This is the distal end. And you've got the condyles here, the medial and the lateral condyle, where it connects with the tibia. But you see that it's overall longer and angled inward towards the knee. We call that a bicondylar angle. And you see the chimp femur over here is shorter and straighter. Also the greater trochanter, that's the bump at the proximal end. The greater trochanter in the modern human is going to be more developed. It's actually this one has kind of broken off here. Probably need to find a better picture, but in general, the greater trochanter is far more developed in the biped versus the quadruped. And you also see that there's a little bit of an angle where the neck of the femur goes into the head of the femur here. Whereas in the chimp, the neck is shorter and it's much straighter as well. Questions so far? All right, the phalanges. Okay, so the phalanges, we have the same name for the finger bones and the toe bones. Oh, sorry, guys. I don't know why it skipped ahead so many slides. Okay, hold on. Let me get back to the right place. Okay, here we are. All right, the hallux is the big toe, and the phalanges are referring to the other toe bones. So in a quadruped, we see an opposable hallux. So when you're looking at these images here, this is Artie here, this is Ardipithecus, this is Homo habilis, this is a modern human, and then this is a chimpanzee. So a chimpanzee and Artie will still have that opposable hallux. So that's a retention of that ability to be arboreal, to locomote in the trees. You'll also notice that the phalanges are longer and more curved. And in the bipeds, we have a hallux that has rotated to be in line with the rest of the toes. And when you think about the way that we locomote bipedally, our big toe is really a big part of our locomotion. Our big toe is kind of that springboard, what we use to push off. So our hallux, our big toe, is in line with the rest of our toes. And we also have ligaments that bind our foot into arches. We call that double arches, and also that it serves as a shock absorber. All right, so the big parts of the skeleton we looked at: the foramen magnum, the shape of the vertebral column, the shape and angle of the pelvis, the length and angle of the femur, and also the feet. Those are some of those big changes that happen as we transition to bipedal locomotion. All right, questions about the anatomical changes? Okay, let's talk about the hypotheses. So these are basically what scientists, what anthropologists, what they came up with when they were trying to determine essentially why did we make this decision? Why was it more advantageous for us to transition away from being arboreal and quadrupedal in favor of being more terrestrial and bipedal? So, like I mentioned, one of the earliest hypotheses that came out in the 1970s was the savanna hypothesis. Because in the 1970s, that's when Lucy was discovered. Lucy is an Australopithecine that we will talk about later on in this lecture. But she was discovered and dated to about 3.5 million years ago. And we know that around that time, the continent of Africa went through this cooling and drying spell. So it caused major changes to the landscape. So it changed the entire landscape of Africa. All of a sudden, we see the mixed woodlands disappearing, and we see open grasslands and savannas expanding. So this is caused by the continental plates splitting apart, causing these major landscape changes, overall drying and expansion of the grasslands or savannas. So you'll see those terms used interchangeably. Grassland and savanna just means an environment that's more open and has tall grasses. So the savanna hypothesis is basically stating that the transition from arboreal quadrupedalism to terrestrial bipedalism was predominantly due to this habitat change, this habitat shift, that the forests were diminishing, the grasslands were expanding. So it was beneficial for our ancestors to stand bipedally so that they could see over tall grasses, to identify food sources, to avoid predators. That was the big hypothesis that emerged around this time. All right, now we do know that this hypothesis, at least in its purest form, is not necessarily 100% correct. Because in the 90s, when they discovered Ardipithecus, and then in the early 2000s, they discovered Sahelanthropus, that we'll talk about here in a moment. But essentially, we discovered that bipedalism predated the expansion of the grasslands. So the earliest bipeds were not living on the open savanna. The earliest bipeds were living in a mixed woodland habitat. So that forced us, the discovery of these pre-australopithecines forced us to kind of throw out this classic savanna hypothesis. All right, now there's many other theories that we'll go over. The patchy forest hypothesis, this one came out in the 1980s, developed by Peter Rodman and Henry McHenry. This one stated that bipedalism arose in areas where forests were fragmented and food resources also became scattered. So essentially, it's looking at this mixed habitat and saying that as forests fragmented, bipedalism freed the hands to pick up food, allowing for both tree and ground food resources to be exploited. So again, we're still looking at the habitat here, but this is acknowledging that our earliest ancestors did not exist just on the savanna. Our earliest ancestors also existed in mixed woodland habitats. So, and when you think about it, if our earliest ancestors were able to locomote in the trees and on the ground, that means that they were able to exploit food resources in both of these locations. They could exploit food resources on the ground and in the trees. They could avoid predators by going in the trees or on the ground. So this one I think is, a possible explanation. It definitely acknowledges the mixed habitats that our early ancestors were living in and acknowledges the benefit that our ancestors would have if they were able to exploit resources in both places, essentially. All right, so that's the patchy forest hypothesis. Questions so far? All right, the next one is called the thermoregulation hypothesis. This one is looking at the kind of biomechanics of essentially bipedal locomotion and how they were potentially able to expel heat more effectively as bipeds. So bipedalism was favored to manage body temperature and stay cool during the heat of the day. The upright body temperature would have lifted, or the upright body posture, upright body posture would have lifted much of the body into the slightly cooler zone of air, and also exposing bodies to more wind and air to help cool them down. And additionally, when you're this quadrupedal stature, when you're locomoting quadrupedally, your entire head and your entire back are exposed to that solar radiation. Whereas when you're standing bipedally, it's just the top of your head and your shoulders really that are exposed directly to this UV radiation. So essentially looking at just body posture and how that could be more effective at expelling excess heat and staying cool in the African sun. This one also has some problems because of the same reason of the savanna hypothesis, because since we now know that bipedalism much more likely emerged in a mixed woodland habitat instead of the open savanna. If these early hominins were in a mixed woodland, they would have been able to use the trees and the canopy to help shade them from the hot African sun. So it's not very likely that this is the primary or the original reason that we transitioned to bipedalism, but it's possibly a factor. In my opinion, there's probably not one answer to this question. There's likely many reasons why ultimately it was advantageous for us to be bipedal over quadrupedal. There were probably many reasons, but this is one that also has some problems if you're looking at it as the primary reason. All right, provisioning hypothesis. So this one was developed by Owen Lovejoy. This one looked at freeing the hands as being advantageous or important in allowing males to assist females in more efficiently procuring or provisioning food. So essentially looking at the fact that having open hands, freeing our hands would allow us to more effectively gather, picking up fruit, vegetation, anything that we could to help support the caloric demands not only of ourselves, but also for females, since females have especially high caloric demands. They're not only supporting their own body, but also needing to support their offspring. So provisioning essentially acted as a form of sexual competition amongst males for females. The better they could be at provisioning food, at gathering food, the more pressure they could take off the females, the more likely they would be to have a high level of competition and high level of reproductive success. So according to this hypothesis, being bipedal and being able to more effectively procure food and provision food would allow birth spacing to be reduced, since females would have to move around less and would have greater access to food resources. So birth spacing, remember, is just that period of time between birth A, birth B, birth C, so on and so forth. And we know that in general, for hominins and even for apes, it's not advantageous for us to have a birth every year. It is more advantageous for us to space out our births several years, okay? Because our infants are born so dependent upon us for survival, we have to invest a great deal in the survival of each offspring. It would not be beneficial for us to have a 1-year-old, an infant, and a 2-year-old and a 3-year-old and trying to take care of all of them at the same time. It just simply wouldn't be effective. So it's much more advantageous for us to space out our births at least 3 to 5 years. All right, the postural feeding hypothesis. This one was developed by Kevin Hunt in the 1990s. This one looks at feeding benefits associated with bipedalism, and it's actually looking at the possibility that bipedal posture and locomotion originated in the trees rather than on the savanna. It looks at the upright posture that you see in modern day apes, such as chimpanzees. So you oftentimes see modern day apes standing bipedally on stronger branches to reach higher hanging fruit. So it's looking at that possibly this bipedal posture originated when our ancestors were still predominantly in the trees, because we often see modern day apes stand in this way to reach hanging fruit and the small trees that are typical in the African woodland environment. And it hypothesizes that early hominins became upright to stand on tree branches to collect fruit, and that upright walking on the ground came much later. So I think this hypothesis really goes along nicely with some of the discoveries that were made in the 90s and 2000s of the pre-australopithecines that we're going to talk about here in a moment. But we now know that the earliest ancestors were likely doing both. They were likely locomoting in the trees and on the ground. So having this kind of habitual transitional form of bipedalism really would have been a benefit. So this postural feeding hypothesis, along with the patchy forest hypothesis, really kind of allow for this, mixture of environments, this, mosaic environment. All right, questions about some of the hypotheses. Now that's, not an exhaustive list, but there's a few other hypotheses to talk about. But those are kind of some of the big four or five that they really use to kind of explain why we might have transitioned. All right, so let's talk about some of the pre-australopithecines. So this term pre just means before. So we're going to look at groups of hominins. The main groups we'll look at the pre-australopithecines. Then we'll look at the robust and gracile australopithecines. And then once we get into chapter 10 and 11 and 12, we'll look at early members of genus Homo and then later members of genus Homo. So the pre-australopithecines exist between about 6 million years ago to as recently as 4 million years ago. And it's really just three species. It's Sahelanthropus chilensis that existed from 6 to 7 million years ago, Orion tugenensis that's dated to about 6 million years ago, and Ardipithecus rhomboides that dates about 5.8 to 4.4 million years ago. All right, so these are what I call kind of species summary slides. So this one here is for Sahelanthropus chilensis. Now, I know these are big, long, scary words, and actually it's really the pre-australopithecines that are the toughest, and the australopithecines. Once we get into genus Homo, it will get easier. But I do encourage you, you guys are all at home and you guys have yourself on mute. When I say these words, I encourage you to practice saying them with me, because learning how to pronounce them will make them easier to understand, easier to spell. And this one's probably the toughest. I love that they, well, not love, but it's interesting that they make the toughest one kind of the earliest one. But this is Sahelanthropus chilensis, Sahelanthropus chilensis, Sahelanthropus chilensis. So this means southern ape from Chad, essentially. Chilensis is Chad. So Chad is a country in Central Africa. This particular fossil is important because it is believed to be very close to that divergence. The date of this fossil, essentially how old it is about 6 to 7 million years old. So that's essentially the oldest hominin, the oldest fossil hominin we have discovered to date. So in order to qualify as a hominin, it needs to have certain features. It needs to be at least a habitual biped. So features like the foramen magnum needs to be more anterior, more underneath at the base of the skull. Non-honing canines are another hominin feature. Now, for this fossil, there is some debate. There are some anthropologists that feel that Sahelanthropus chilensis is more likely a pongid than a hominid. But it's debatable. But we bring it up because it is the earliest one that shows evidence of bipedalism. So the habitat for this species, where it was found, would have been forested near a lake. The cranial capacity is still relatively small. So to give you a comparison, modern humans have a cranial capacity anywhere from 1,400 to 1,700 cc's. So Sahelanthropus chilensis has a brain size about a fifth of the size, just barely bigger than what you would see in a modern day chimp, about 350 cc's. Okay, likely a habitual or part-time biped because the foramen magnum is in a more anterior position towards the front of the skull. Non-honing chewing. So we talked about that a little bit in previous chapters, but we've got the gorilla here to show you a comparison. We've got these massive canines, and we also have spaces in between the canines and that first premolar that allows the jaw to open and close, essentially. So it makes room for those canines and allows for opening and closing of the jaw. So non-honing in comparison, so this would be honing. So non-honing canines are canines that are drastically reduced in size. So smaller canines. And we do not have, as hominins, we do not have a space in between that canine and the first premolar. Okay, so there's non-honing canines, the lack of a diastema. So that's the two main reasons why Sahelanthropus is categorized as a hominin instead of a pongid is the smaller, reduced canine size and the non-honing nature of the canines. Sahelanthropus also has this, kind of ape-like feature with a more pronounced, larger, massive brow ridge. And there's also quite a large degree of postorbital constriction. And there's also the remnants of what is probably a sagittal crest right here. All right, so this is just one of those summary slides. We've already talked about this information, but I put these slides here to kind of give you a summary of each species. And this is kind of a better picture of it here as well. So this is from a company called Bone Clones that makes all these replicas. So they are replicas of the actual fossil that allows us to be able to study them. So the nickname for this fossil is Tumai. The species is Sahelanthropus chadensis. Sahelanthropus chadensis. The date range for this species is between 6 to 7 million years old. Discovered in the country of Chad, which is in Central Africa. So the features, likely a habitual biped based upon the position of the frame and magnum, but would have been very close to that divergence between the hominids and the other great apes, the pongid hominid divergence, a mosaic or mixture of hominid and pongid-like features, massive brow ridges, and a relatively small cranial capacity, around 350 cc's. No questions about Sahelanthropus chadensis?
No, but could you say it again?
Sure, this one is Sahelanthropus chadensis. Let's say it together a few times. I encourage you guys at home, put yourselves on mute and say it together with me. This is Sahelanthropus chadensis. Sahelanthropus chadensis. And one more time, Sahelanthropus chadensis. So this is nicknamed Tumai. All right, good question. Any other questions about Sahelanthropus chadensis? All right, let's talk about the next one that we consider a pre-australopithecine. This is Orion tuganensis. Orion tuganensis. Orion tuganensis. So this one was discovered in Tugan Hills in Kenya, some more eastern Africa. The date of the species would have been about 6 million years old. Habitat would have been forested. Anatomical features, and we only have the femur, but remember the femur is a part of that skeleton, the part of our skeleton that really does help us determine locomotion. So even though we only have a femur from this species, it is very indicative of at least habitual bipedalism. So in this picture here, you see a recreation of a modern human femur. We're looking at a posterior view or a view from behind, the back of the femur. And then you see Orion here in the middle, and then a chimpanzee all the way here on the right side. So see here, the fully modern human has a longer, more angled neck of the femur, whereas the chimpanzee is short and straight. And you see it's much more like the modern human here in Orion. You also see that there's a little bit of an angle here, that it's likely more angled like the modern human. So Orion tuganensis is generally given the bipedal classification due to that shape of the femur. All right, the next pre-australopithecine is Ardipithecus rhomidus. Let's say it together a few times. This is Ardipithecus rhomidus. One more time, this is Ardipithecus rhomidus. So I already gave you a little bit of a window, a little bit of a peek on the species when we watched the first film clip for today. Because Ardipithecus is really a great example of that habitual or part-time transitional bipedalism. they discovered about 80%, or they were able to recover about 80% of Artie's skeleton, which is huge, a huge amount of skeletal material considering how old this hominin is. So the Ardipithecus ramidus specimens, this individual lived about 4.4 million years ago, and the habitat would have been a mixed woodland or forested habitat, like they demonstrated in the video clip. And because they uncovered such a large proportion of the skeleton, they really were able to recreate basically how this hominin would have looked. Okay, so they know that the cranial capacity is relatively small, so barely bigger than what you would see in a modern day chimpanzee, right around 380 cc's for Ardipithecus. The foramen magnum is more at the base, so the foramen magnum is positioned more like a biped. You do see that S-shaped spinal column there. You see that the rib cage is kind of actually like you would see in an ape, so a broader rib case in comparison to what you might see in a modern human. You notice that the arms are long, so that's a feature thinking back to our locomotion section, our primate locomotion section. The longer arms, that's characteristic of what you would see in a brachiator. Remember, that's that form of locomotion where they swing from branch to branch using their arms. Also, the curved fingers, the longer curved finger bones, the phalanges, that's an adaptation that allows them for more effective gripping. And then the pelvis, like we talked about in the video clip, the top half is kind of rounded and bowl-shaped like you'd see in a modern-day biped. But the bottom half, the ischium, is longer, like you would see in a quadruped. The femur is longer and angled inward towards the knee, like you'd see in a biped. And then the feet, notice that opposable hallux here. So it really is kind of half and half. Kind of half of those features are something you would expect to see in a biped, and the other half of those features are something you would expect to see in a quadruped. So it really is, like they mentioned in the film, it really is a creature in transition, which I find absolutely fascinating because you really, I'm sure you've heard people argue that there's no transitional fossils, that's why there's no evidence for evolution, is that you don't see transitional fossils. We actually do. We have lots of fossils in the fossil record that are somewhat transitional and indicate that obviously this transition from quadrupedalism to bipedalism did not occur overnight. It took about 4 million years because we see these earliest bipeds are very mosaic. Other features of Artie. So this is Ardipithecus ramidus. Let's say it together a few times. This is Ardipithecus ramidus. Ardipithecus ramidus. One more time. This is Ardipithecus ramidus. So nickname, you're going to hear it called Artie. 4.4 million years ago, discovered in the Afar region of Ethiopia. So we're talking Eastern Africa here. Discovered by Tim White in 1994. But when you look at papers, you're going to see it's probably not published for about a decade after that. So early 2000s. Cranial capacity, relatively small, just a little bit bigger than Sahelanthropus, about the size of what you'd see in a modern day chimp. So that's another thing that we're going to see is all these early bipeds, even the Australopithecines, do not have a massive brain size. So we're not really going to see a huge jump in cranial capacity until we get to Homo erectus. So we know that bipedalism predated expansion in cranial capacity by several million years. So Artie was a habitual biped or part-time biped, retaining some degree of arboreal capabilities. Arms and legs of approximately equal length, but that's long arms essentially, because in modern humans, it's the opposite. In modern humans, our legs are much longer than our arms. But you know that Artie had that retention of brachiation due to the longer arms, or at least some degree of brachiation abilities. Opposable hallux or big toe, smaller non-honing canines. So look at that canine there. It's a little bit bigger than what you might see in a modern human, of course. It's a little bit pointier. But you see that it's not anywhere nearly as large as what you would see in our gorilla friend here. Our gorilla friend has massive canines and also has that space in between the canines and the first premolar, that diastema, that allows for the jaw to open and close. So smaller non-honing canines, and overall relatively small cranial capacity in comparison to modern day humans. So we'll say this together a few more times. This is Ardipithecus ramidus. Ardipithecus ramidus. One more time, Ardipithecus ramidus. Do we have questions about Artie? Feeling good? All right, so that's kind of a good place to stop for right now, because we went over the anatomical adaptations for bipedalism. We went over the different parts of the skeleton that we look at when we're determining biped versus quadruped. We talked about the various theories on bipedal locomotion. And then we talked about the very first 3 species on our evolutionary tree, essentially. So we have a little bit of time in breakout rooms today. So what I want you to do is just, I want you guys to help each other out with your concept review questions. So, go over the questions that we've talked about so far and help each other out. So we have about 10 minutes to do that in breakout rooms today. I'm going to go ahead and stop the recording.